Okay. Thank you, Professor Mastorakis, for your presentation. My name is Michael Voskoglou. I am an emeritus professor of mathematical science of ex-graduate Technical Educational Institute of Western Greece, and now is named as University of Peloponnese. And I'm going to speak about Neutrosophic assessment and decision making. The theory of Neutrosophy, introduced by Smaragdaki in 1995, is an extension of Zadek's fuzziness. The term Neutrosophy, formed by the synthesis of the words neutral and the Greek sophia, which means wisdom or complete knowledge. As we will see in the detail, in the next section, in a Neutrosophic set, all the elements of the universal set of the discourse are characterized by three parameters which take values in the unit interval 0, 1. Neutrosophic sets have found important applications to practical everyday life problems in which the use of the Zadek's fuzzy sets has not been proved to be sufficient for obtaining the required results. The purpose of this work is to present applications of Neutrosophic sets to assessment and decision-making processes. Let's start with the mathematical background, which is necessary for the understanding of this work. And first, about fuzzy sets. Zadek, in order to tackle mathematically the existing in real life partial truths, defined in 1965 the concept of fuzzy set, which is defined as follows. Let U be the universal set of the discourse. Then a fuzzy set A in U is defined with the help of its membership function, which sends U to the unit interval, as the set of all ordered pairs of the form 1. The real number mx is called the membership degree of x in A. The greater mx, the more x satisfies the characteristic property of A. There is not any exact rule for defining the membership function of a fuzzy set. The methods used for this are usually empirical or statistical, and its definition is not unique, depending on each observer's subjective criteria about the corresponding situation. Defining, for example, the tall set of the tall men, one may consider as tall all men with heads greater than 190 meters, and another all those with heads greater than 2 meters. As a result, the first observer will attach membership degree 1 to all men between 190 and 2 meters, whereas the second one will attach membership degree less than 1. Analogous differences may obviously appear to the membership degrees of the men with heights less than 190. Consequently, the only restriction in the definition of the membership function of a fuzzy set is that it must be compatible to the common sense. Otherwise, the resulting fuzzy set does not give a creditable description of the corresponding real situation. This could happen, for instance, if in the previous example, γιατί δεν πάει εκεί το. Ναι, με το ποντίκι, αλλά δεν βγαίνει το βελάκι. Τώρα βγήκε. Okay. If in the previous example, men with heights less than 160 meter possessed membership degrees greater than half. In a later stage, when membership degrees were reinterpreted as possibility distributions, fuzzy sets were extensively used for managing the existing in real life uncertainty, which is connected with incomplete or vague information. Possibility is an alternative mathematical theory for tackling the uncertainty. Zadeh articulated the relationship between possibility and probability by noticing that whatever is probable must be primarily possible. All notions and operations defined on crisp sets are extended in a natural way to fuzzy sets, and for general facts on fuzzy sets, we with the connected to them uncertainty, refer to the classical book of Clear and Forger, 1988. Now about Neutrosophic sets. Following the introduction of fuzzy sets, a series of extensions and related theories have been developed for tackling more effectively all the forms of the existing uncertainties. Atanasov in 1986 added to Zadeh's membership degree the degree of non-membership and defined the concept of intuitionistic fuzzy set as an extension of fuzzy set. Smarandake in 1995, motivated by the various neutral situations appearing in real life, like positive, zero, negative, small, medium, high, win, draw, defeat, etc., introduced, in addition to the degrees of membership and non-membership, the degree of indeterminacy, and extended the concept of intuition in fuzzy set to the concept of Neutrosophic set. In this work, we will make use only of the simplest form of a Neutrosophic set, termed as a single valued Neutrosophic set, which is defined, again the problem with as follows. A single valued Neutrosophic set A in the universal set U is defined as the set of all the ordered tuples of the form 2. In 2, Tx, Ix, and Fx are the degrees of truth or membership, indeterminacy or neutrality, and falsity or non-membership of X in A respectively, called the Neutrosophic components of X. Excuse me. For simplicity, we write A in the form TIF and the elements of A in the form TIF small letters of Neutrosophic triplets, as Neutrosophic triplets, with of course TIF in the unit interval. Let's see an example. Let U be the set of all players of a football team, and let A be the Neutrosophic set of the good players of U. Then each player X of U is characterized by a Neutrosophic triplet. For instance, the player X characterized by the Neutrosophic triplet 0.7, 0.1, 0.4 means that X that there is a belief, 70% belief that X is a good player, 10% doubt about it, and at the same time, a 40% belief that X is not a good player. In particular, if 0, 0, 1, 0, 1, 0 is a Neutrosophic triplet, this means that we don't know nothing about the X's affiliation with the Neutrosophic set A. When the sum Tx plus Ix plus Fx is less than 1, it leaves room for complete information. When it is equal to 1 for incomplete information, sorry, for complete, in the first case for incomplete, in the second case for complete information, and when is greater than 1 for inconsistent information about X in A. A characteristic of a single-valued Neutrosophic set is that it may contain simultaneously elements corresponding to all kinds of the previous information. That is, all kinds of the previous types of uncertainty. All notions and operations defined on fuzzy sets are extended in a natural way to Neutrosophic sets. Since the Neutrosophic triplets of a single-valued Neutrosophic set are ordered triplets, one may define addition among them and scalar multiplication of a positive of a positive number with a Neutrosophic triplet in the usual way. Oh, this is always. I'm losing the. Sorry. I don't know. Huh? Anyone? Ah, thank you very much. So, let T T1 I1 F1, T2 I2 F2 be in A, and let R be a positive number. Then the sum of the two Neutrosophic triplets is defined by 3, by equation 3, and the scalar product of R by Neutrosophic triplet by equation 4. We may notice that the sum and the scalar product of the Neutrosophic triplets of a Neutrosophic set with respect to definition 3 need not be a Neutrosophic triplet of A. That is, the previous operations are not closed operations in A, since it may happen that T1 plus T2 I1 plus I2 plus F1 plus F2 bigger than 3, greater than 3, or RT1 plus RI1 plus RF1 bigger, greater than 3. With the help of definition 3, however, one can define the mean value of a finite number of Neutrosophic triplets of A, which is always in A. This is a closed operation, as follows. Let A be a Neutrosophic set, and let consider K and Neutrosophic triplets of A finite number. Assume that the first one appears n1 times, the second A2, etc. Then the mean value of all these elements of A is defined to be the Neutrosophic triplet defined by the equation 5. Now, about soft sets. The disadvantage of Neutrosophic sets concerning the definition of their membership function remains obviously the same for all extensions involving membership degrees, like the intuition fuzzy sets, the Neutrosophic sets, and other extensions. To overcome this difficulty, the concept of integral-valued fuzzy set was introduced in 1975. Such a set is defined by mapping the universe to the set of the closed subintervals of 0, 1. That is, instead of a number in 0, 1, we define to a subinterval in 0, 1. Other related to fuzzy set theories were also developed in which the definition of the membership function is either not necessary, like the Greek systems and the Greek numbers, or it is overpassed by using a pair. Sorry, what happened? Sorry, this time. How I go back to. I passed over the. Uh, uh, oh, it's okay now. Soft sets, yeah. The disadvantage of neutrosophic sets concerning the definition of their membership function remains obviously the same for all their extensions involving membership degrees. I said this and I speak about the Greek systems and the interval valued fuzzy sets, and another kind of, this kind of extensions are the raft sets, which they use a pair of concepts given the lower and upper bound of the original set. Molotov introduced in 1999 the definition of soft set by tackling the uncertainty in a parametric manner, which does not need the definition of the membership function. Namely, a soft set is defined as follows. Let E be a set of parameters and let F be a map from me into the power set of all subsets of the universe U. Then the soft set F comma E in U is defined by equation 6. In other words, a soft set is a parameterized family of subsets of U. The name soft is due to the fact that the form of the soft set depends on the parameters of A. An example, let U be a set of 3 cars and let E be the set of the parameters E1 cheap, E2 elegant, and E3 expensive. Let us further assume that S1, S2 are cheap, S3 is expensive, and X2, S3 are elegant cars. Then a map F is defined by the equations you see, and the fuzzy set Fe is this shown in equation 7. Maggi et al. Introduced a tabular representation of a soft set in the form of a binary matrix in order to be stored easily in a computer's memory. For instance, the tabular representation of the previous soft set is shown in table 1. A fuzzy set in U with membership function y is equal mx is a soft set in U of the form f comma 0, 1, where fa all x of U such that mx greater than a is the corresponding a cut of the fuzzy set for each a in 0, 1. Consequently, the concept of a soft set is a generalization of the concept of a fuzzy set. All notions and operations defined in fuzzy sets are extended in a natural way to soft sets. And now we going to the main part of our work, starting with the Neutrosophic assessment. The performance of the members of a group is assessed frequently by using qualitative grades, that is, linguistic expressions, instead of numerical scores. This happens either because the existing data about their performance is not very clear or for reasons of elasticity. For example, when a teacher wants to be more elastic to his students. Obviously, in such cases, the mean performance of the group cannot be assessed by calculating the mean value of the individual scores of its members. For tackling these situations, we have used in earlier works either triangular fuzzy numbers or green numbers, that is closed real intervals, and we have shown that these two methods are equivalent. Cases appear, however, in practice in which one is not sure about the accuracy of the qualitative grades assigned to the objects under assessment. In such cases, the use of Neutrosophic sets is possibly the best way for evaluating a group's overall performance. The following example illustrates this situation. Assume that a teacher is new for a student class and he is not sure yet about the quality of each of the students. He decided, therefore, to characterize the very good students of the class by Neutrosophic triplets as follows. S1 by Neutrosophic triplet, which is 1, 0, 0, S2 0.9, 0.1, 0.1, etc., up to S10. And the remaining 10 students, all the students of the class were 20, by 0, 0, 1. This means that the teacher is absolutely sure that S1 is a very good student, 90% sure that S2 is a very good student too, but at the same time, he has a 10% doubt about it, a 10% belief that it may not be a good student. For the last 10 students, the teacher is absolutely sure that they are not very good students. How we can evaluate the overall performance of the student group in this case? The mean level of the student skills can be estimated by the mean value of the corresponding Neutrosophic triplets, which according to the equation given previously in the mathematical background, and it is found to be the triplet 0, 2, 2, 5, 0, 2, 6, 5, 0, 8, 1, 5. This means that a random student of the class has a 22.5% probability to be a very good student. However, there exists also a 26.5 doubt about it and a 81.5 probability to be not a very good student. This is about Neutrosophic assessment, and now we go to the Neutrosophic decision making. Maggi et al. Used the tabular form of a soft set as a tool for decision making in a parametric number. The following example highlights their method. A person wants to buy one of the 6 cars, S1, S2, S3 up to S6. His ideal preference is a high-speed automatic in the gearbox, hybrid running with petrol and electric power, and cheap car. Assume now that S1, S2, and S6 are the high-speed cars. S2, S3, S5, S6 are the automatic, S3, S5 are the hybrid, and S4 is the unique cheap car. Which is the best choice for the candidate buyer? In this case, we consider as the universal set the set of all cars, and as the set of parameters C, E1 high speed, E2 automatic, E3 expensive, and E for cheap. And then a map is defined, G from me to E, which gives genesis to the soft set of equation 7. The tabular representation of this soft set is shown in table 2. Forming the tabular representation of the soft set, the choice value of each car is calculated by adding the binary elements of the corresponding row of it. The cars S1 and S4 have choice value 1, and all the others have choice value 2. Consequently, the buyer must choose one of the four cars, S2, S3, S5, or S6. The previous decision obtained by applying the method of Maggi et al. Is not very helpful because the candidate buyer, since it excludes only two among the six, because it excludes only two among the six available cars. This is due to the fact that in the tabular form of the corresponding soft set, the characterizations of the elements of the universal set, cars, for example, uh, with the corresponding parameters, in this characterization, the corresponding parameters are replaced with binary elements. That is the truth value 0, 1. In other words, although their method starts from a fuzzy basis, soft sets, it uses bivalent logic for making the required decision. For example, cheap or not cheap. Consequently, this methodology could lead to a wrong decision if some or all of the parameters have not a bivalent texture. For example, the parameter hybrid has a bivalent texture, but not the parameter cheap. In order to tackle this problem, we have used in earlier works green numbers instead of the binary element 0, 1 in the tabular representation of the corresponding soft set. Decision-making situations, however, appear frequently in reality in which the decision maker has doubts about the correctness of the uh, qualitative characterizations assigned to some or to all of the elements of the set of the discourse. In such cases, the best way to perform the decision-making process is the use of Neutrosophic sets. This is illustrated by example 5. We reconsider example 4 and we assume that the candidate buyer be not sure about the correctness of the qualitative parameters A1 and A4, which are of fuzzy texture, assigned to each of the six cars has decided to proceed by replacing the parameters 0, 1 by Neutrosophic triplets. As a result, the tabular matrix of the decision-making process takes the form shown in table 3, where all the Neutrosophic triplets give complete information about the corresponding car. And this happens because the sum of the three components is equal to 1. Now, which is the best decision for the candidate buyer? Again, the philosophy of the method is the same. We calculate the choice value of each car, but in this case, by adding Neutrosophic triplets and not by adding 0 and 1. We have already defined previously the mean value of the Neutrosophic triplets, and we calculate the mean value of each line of table 3. Thus, by the previous equation 5, the choice value of S1, after all making all the calculations, is equal to 0.4, 0.075, 0, 5 to 5. In the same way, one finds the choice values of all the other cars. Now, the candidate buyer may use either an optimistic criterion for choosing the car with the greatest truth degree or a conservative criterion by choosing the car with the lower falsity degree. Consequently, using the optimistic criterion, he must choose one of the cars S3 or S5 because these have the greatest truth degree. Whereas using the conservative criterion, he must choose the car S3. Now, a combination of the two criteria leads to the final choice of the car S5. Observe, however, that since the indeterminacy degree of S3 is 0.15 and of S5 is 0.1, there is a slightly greater doubt about the suitability of S3 with respect to S5. In other words, the choice of S3 is connected with a slightly greater risk. In final analysis, therefore, all the Neutrosophic components assigned to each car give useful information about its suitability. And you see, in this case, the method of magic all decided to ended with the final conclusion to choose one out of four cars, while when we use the Neutrosophic sets, we have just one choice, one car, which is much more helpful. We are closing with the discussion and conclusions. In this work, Neutrosophic sets were used as tools in assessment and decision-making processes. This is very useful when one is not sure about the correctness of the parameters or the qualitative grades in state of parameters in assessment processes assigned to each of the elements of the universal set. Our decision-making method in particular was obtained by adapting a parametric decision method of Medj et al. Using soft sets as tools. In our method, the binary element 0, 1 of the tabular representation of the corresponding soft set are replaced by Neutrosophic triplets. The combination of two or more extensions of fuzzy sets that have been developed for tackling efficiently the various forms of the existing real-world uncertainty. In this paper, we use soft sets and Neutrosophic sets, appears in general to be an effective way for obtaining better results, not only for decision making, but also for assessment and possibly for various other humans activities. Consequently, this is a promising area for further research. That is, to combine two or more generalizations of fuzzy sets to obtain the required results. A table with 18 references, I think, follows. And we are close with an appendix about a special issue that where I am guest editor in the journal Mathematics of ME-DPI. This is called Advances and Applications of Soft Computing. Soft computing is a part of computer science, including, apart from fuzzy sets and logics and their extensions, probabilistic reasoning, neural networks, and genetic algorithms. And this is a flyer for the journal Mathematics, where this special issue belongs. And I have some leaflets to disturb to you. I'm just doing it now. about this special issue, and I have also my email written, and if you are interested, you may contact me or write continuously to write directly to the journal. Thank you for your attention. Ah, please.